This lesson looks at stoichiometry, specifically involving concentration. So now that we've done some calculations of concentration, we're going to take a look at how concentration can be used to find moles and do mole ratios. And so if you remember, when we were talking about molar concentration, we had C equals N over V. That was our molar concentration that we used, where N was the number of moles, V was the volume of solution, and C was our concentration. But we can rearrange that, right? So we can rearrange it to find moles so that moles is equal to C times V, right? So now we've got a way to find moles when we're dealing with concentration, which means in a stoichiometry calculation, we've got another way to find moles. So anytime we do a concentration calculation, we just need to remember our steps, right? We have 4 steps to doing these concentrations. And the first step is our balanced chemical equation, right? So that's our BCE. The second step we talk about is our convert to moles, or CTM, sometimes we shorten it that way. So we want to convert to moles. And then the convert to moles step always is based on whatever substance you have enough information about to find moles of. And then it's the next part where the stoichiometry really comes into play. The stoichiometry is all about the mole ratio, right? So that's what this part is all about. It's about the mole ratio. And there are 2 scenarios where we might deal with a mole ratio. We might deal with the mole ratio to find limiting reagent or limiting reactant. The other one is we'll just use the mole ratio if we don't have to worry about limiting reactant because we know something's in excess already. Then we just use it to find the moles of the substance that we want. So once we've got our mole ratio step complete, it means we'll have found the moles of the substance that we're looking for. And then the last step is to convert to a specific unit. So if you remember our specific unit, that could be mass unit, so grams, that could be particles. Getting into Avogadro's constant again, we could get into concentration of something, even volume of a solution. There are lots of different things we could look at. And as we go further in the course and we start talking about gases, we'll get into that as well. But these are our 4 steps. So any stoichiometry problem we do, this is what we want to make sure we're following. So let's try a couple of examples here and see what we can do. So the first example we'll look at will be this one. These are some sort of common type questions we might see as we're going along. It says determine the molar concentration of chlorate ions if 235 grams of aluminum chlorate known as hydrate is dissolved in water to create a 2-liter solution. So this is an ionic substance. So remembering ionic substances, when we put them in water and they become aqueous solutions, right, they dissociate, which means they break into the ions. So if we start with this substance and we put it into water, we're going to end up with an aluminum 3+ ion in solution. That's the AQ. We're going to end up with chlorate ions in solution. And we're going to end up with water, right? This is a hydrated salt, so you'll see that there's water present. So we're going to end up with 9 waters because we have 9 H2O. We're going to end up with 3 chlorates. So when we balance this, there'll be a 3, and we'll end up with 1 aluminum. So this is our balanced equation for the dissociation of this particular hydrate salt. Now, once we have the dissociation equation like this, now it just becomes like any other stoichiometry problem. We have to work through our steps. We've got the balanced equation. Now we're on to converting to moles, right? So I'm just going to write CTM. That's our next step. So we're on step 2. Step 1, we've got our balanced equation. So if I think about what we've got with this problem, we have a mass given to us of 235 grams. We have a molar mass given, right? Now remember, molar mass we can get as long as we know our chemical formula. which has all of these pieces in that salt, we can find the molar mass. We just look at our periodic table. We're going to take the mass of 1 aluminum, the molar mass of 3 chlorines, the molar mass of 9 oxygens, and then we need to also include the water. The water is part of this salt. So we're going to need 9 times 2, that's 18 hydrogens, and 9 more oxygens. So when we end up finding the molar mass of this salt, we're going to get 439.51 grams per mole. So that is the molar mass of the salt. Our goal in this problem is to find the concentration of the ion, right? So we want this concentration. We're going to need moles and we're going to need volume. Volume is given as 2.00 liters. So this is sort of what we're working with. Remember, it's going from moles of what we have, which is our salt, to moles of the chlorate ions is how we're going to connect these two. And that is based on the stoichiometry. It's based on that ratio between the salt and the ion. So if we're going to convert to moles, we know we're working with our salt. That's the only information we have. So we're going to find moles. Moles equals mass divided by molar mass. So it's going to be 235 grams divided by 439.51 grams per mole, which gives us a number of moles of 0.534636 moles. Right? Now, thinking about significant digits later on, this number has 3 significant digits. My molar mass has 5, so I'm carrying 3 significant digits. So I'm just going to underline that 4, so it's my mental picture. Later on, when I look back, I'll be able to quickly recognize how many significant digits I'm dealing with there. The next step is our mole ratio. So our mole ratio, right, we're looking at the salt to the chlorate ion. Right, so that's a 1 to 3 ratio that we're dealing with. So when I'm dealing with this, then I'm going to have 0.53468636 moles times, and now I'm going to multiply by that fraction, which relates to my balanced chemical equation. So I have 1 mole of the salt on the bottom and 3 moles of what I want to find, 3 moles of chlorate ions, right? So those ones come from our balanced chemical equation. The one we want is on top, the one we're getting rid of on the bottom. And when we do the math here, then we're going to get 1.6040591 moles of chlorate ions. Okay, and again, I'm carrying 3 significant digits through there, so I'm just going to underline my 0. Now, the last step, the fourth and final step, is to convert to what we want to find, which is a concentration, right? So I'm just going to write find concentration. So concentration is moles divided by volume. So now that we have the chlorate ion moles, and we know the volume of solution, we can solve this problem. So we've got 1.6040591 moles divided by 2.0 liters, and that is going to give us on our calculator 0.8020295 moles per liter. So to finish it off, the concentration of chlorate ions is 0.802, and then I'm going to use big capital M as a unit. If you see big capital M as a unit, that just means moles per liter. So the final concentration of my chlorate ions is 0.802 moles per liter. Okay, so that's how we can solve that problem. Let's try one other problem. We'll do one more. This one is a single displacement reaction, and we're putting in a certain mass of magnesium. It just says a piece of magnesium in the question, so we don't know the exact mass, but we do know a concentration and a volume of our acid solution that the magnesium is being dropped into. So knowing this, we know right now that from our reaction, magnesium plus HCl produces H2 and MgCl2, that this should be balanced with a 2. So I'm going to balance that. Now I'm done the first step of my stoichiometry problem. I got a balanced chemical equation. Second step is we're going to work to convert things to moles. We know that this is excess, so we don't have to worry about anything relating to Mg. We're focused with the HCl. That's what we know. So we know the volume of this is 350.4 mils, and we know that the concentration of it is 0.250 molar. Now, what we want to find is about H2, the hydrogen gas. We want a mass. That's our goal. We know the molar mass is 2.02 grams per mole. That we just get from the periodic table. And in order to get to mass, we're going to need moles. So we're going to use our stoichiometry to go from moles of HCl, right? If we can calculate that, then we can do our molar ratio to get to moles of H2, and then we can find our mass, right? That's our step. So let's take a look then and convert CTM. We'll convert to moles. So moles equals C times V. We're going to get 0.250 moles per liter. Remember, capital M as a unit means moles per liter. And the volume is 350.4 mils, but we need to make sure it has a liter unit, so I'm going to convert that to liters. So that's 0.3504 liters. And when we calculate the number of moles there, we end up getting 0.0876 moles, right? So that's our moles. I'm just going to write in HCl so that I recognize what that's for. My next step in my solution now that I've got moles, is that ratio to get us to moles of hydrogen, right? So I'm going to just call it mole ratio. That's what I'm looking at. So that mole ratio, HCl to H2, is going to be a 2 to 1 ratio. That's what we're looking at. So I'm going to have my 0.0876 moles HCl, and I'm going to multiply it by my fraction that comes from my balanced chemical equation, right? So now we go 2 moles of HCl from our balanced chemical equation, 1 mole of H2 from our balanced chemical equation. And we do the math, and we're going to get 0.0438 moles H2. Right? So now we've got our moles of H2. The last thing we need to do is convert to mass. Right, so if we remember, mass is just moles times molar mass. So we're going to have 0.0438 moles times 2.02 grams per mole, because remember there's 2 hydrogen atoms for every hydrogen molecule. And that gives us a mass of 0.088476 grams. Now, if we look back at our significant digits, back in the question, this concentration has a number of significant digits of 3, the 2, the 5, and the 0. The volume has 4 significant digits, so through here we're carrying 3 significant digits. And that shouldn't change when I do my mole ratio because the 1 and the 2 from the balanced chemical equation are just counted. And then when I look at my next part of my problem, I know I'm carrying 3 significant digits through there, and there's 3 in my molar mass. So I should end up with 3 significant digits in my answer. So the mass of hydrogen produced is 0.0885 grams. And that's our mass of hydrogen.